Maybe we are supposed to start now. I think more or less time. So it's a great pleasure for me to introduce Emmanuel, though he doesn't need any introduction at all, I think. We are more or less of the same age. Actually, I think he's some months younger than me, but he's a very famous and renowned mathematician. He won a large number of prizes, such as the Siam Outstanding Paper Prize, the Primo Resoden, the Felix Klein Prize, the prize for Blas Pascal, and I think he has been invited speaker in the last ICM conference in Brazil. And so I think it's time for me to stop this presentation. Well, he will speak today of one of his main interests, which is spectral analysis of sub-Riemannian Laplacians and Weyl measures.
Thank you. Thank you very much, Enrico, for your very kind words. And also, I'm very glad to have the opportunity to present a series of works that we are currently doing with Yves Collin de Verdière, who is in Grenoble, in France, and Luc Hilleret, who is in Orléans, also in France. And so our topic is about the spectral analysis of subelliptic Laplacians in the geometric framework of Subremanian geometry, which is, from this point of view, a new topic of investigation in mathematics. So let me explain in few words what is a Subremanian structure. A Subremanian structure is usually defined as a triple where capital M is, let's say, a smooth connected manifold of dimension n. You can think of Rn, of course. D, which is called the horizontal distribution, is, let's say, a field, the span of M vector fields, M smooth vector fields on the manifold M. For instance, I took here some very celebrated examples of Subremanian structures. For instance, imagine that you are in R3, and then at every point of R3, you choose a plane. So you have a field of planes which are given by which are spanned by two vector fields, like the famous 3D contact case, also called a 3D Heisenberg case. The variant of it here is called the Martinet case, or another also very famous example and very much used for PDEs is the Groshin case, Bawendi-Groshin case, which is in R2. And in R2, you take two vector fields, but these two vector fields do not generate the whole plane along x equals 0. This is why you have a kind of degeneracy here that is of interest. So in more general, this is a Subremanian structure, and on the horizontal distribution D, you are defining the so-called Subremanian metric just by requiring that the M vector fields are G orthonormal. Now, let us define the main object of interest, that is the subelliptic Laplacian, the Subremanian Laplacian, that we denote by delta. So here we are given a smooth measure, mu, on M, which is completely arbitrary. We will see that mu plays absolutely no role in the spectral study. And delta is defined as the sum of squares of the vector fields. So for instance, the Groshin Laplacian is defined as the square of dx plus the square of x dy. Okay, so this is the Subremanian Laplacian. You can think that a priori it would depend on the vector fields xi, but it's not true. Actually, the Subremanian Laplacian is a geometric object only depending on the horizontal distribution. the way to see it is that there are several equivalent definitions of it. For instance, you can also define delta as being the Friedrich extension of the Dirichlet integral. Dirichlet integral related to the cometric G star, or also another popular definition is the divergence of a gradient, except that here the gradient that you consider is not the usual Riemannian gradient, but the Subremanian, or also called horizontal gradient, which is defined from the Subremanian metric, which is a degenerate metric. Okay, so these are equivalent definitions. Actually, more generally, we can consider so-called Hörmander operators that are also sum of squares of vector fields, but to which you can add some drift term and also, why not, some term of order 0. These are the celebrated Hörmander operators. The fact is that under the well-known Hörmander's assumption, which stipulates that the Lie algebra generated by the vector fields x1 to xm, I mean the span of all xi, of all Lie brackets, xi bracket xj, and then the iterated Lie brackets, should be equal to the whole tangent bundle, Tm. So this is also known as the Lie algebra generating condition. Under this well-known assumption, Hörmander proved a long time ago in the 60s that this kind of operator is locally subelliptic. I mean, you have local subelliptic estimates saying that you have a gain of Sobolev regularity, a gain which is 2 divided by r. We will see what is r in general. For instance, r equal 2 for the 3D contact case, also for the Grushin case, and r equal 3 for the Martinet case. Let me recall what is r in general. From the general point of view, r is defined as the degree of non-holonomy, meaning that it is the smallest possible integer such that such that with all Lie brackets of length r, you are able indeed to generate the whole tangent bundle. This is the definition of the degree of non-holonomy. For instance, in the 3D contact case, you have these two vector fields, x1 and x2. So you do not generate R3. But to generate R3, you are led to consider the first Lie bracket, x1 bracketed with x2, which gives exactly dz, the missing direction. So here you have r equal 2 because, so it means that degree of non-holonomy is equal to 2. For the Martinet case, what is the difference? We put a square here. We put the x that was here at a square. We obtain the Martinet case. So you see that then we need one further Lie bracket in order to generate the missing direction everywhere in R3. Actually, so it means that we have R equal 3 in general. I mean, along x equals 0, because along x equals 0, the first Lie bracket is degenerate. But outside of this singular surface, which is called the Martinet surface, usually, you have only R equal 2. For the Bawendi-Grushin case, well, this case is perfectly Riemannian outside of x equals 0, because outside of x equals 0, the two vector fields generate the whole R2, but along x equals 0, you need to take a Lie bracket. This is why you have a hypoelliptic configuration there. So, on the previous slide, we consider what is called the Subramanian flag. I mean, this is a filtration of the tangent bundle by the span of the successive Lie brackets. This is the horizontal distribution. This is the horizontal distribution plus the first Lie bracket, and then etc., etc., until you reach the whole tangent bundle. And from this filtration, you can define what we can call the homogeneous dimension at any point Q, which is defined as the sum of I times the difference of two successive dimensions of the filtration. Actually, this integer is always equal to the Hausdorff dimension around the point Q whenever Q is regular. What means Q regular? Q regular means that the Subremanian flag is regular, meaning that the dimensions of the successive elements of the filtration are locally constant. Otherwise, we will say that Q is singular. For instance, the 3D contact case. For the 3D contact case, every point is regular, so we say that the structure is equiregular. But for the 3D Martinet case, or also for the Grushin case, you have a singularity along x equals 0. So in that case, every point along x equals 0 is a singular point. Also, another definition of interest is that we define the so-called Subramanian weights at the point Q. Well, it just means, in a few words, that for all directions that are directly reachable from the horizontal distribution, you put a weight equal to 1. Let me take the example here. For instance, the x variable is directly accessible. So you call, you say that W1 is equal to 1. Also, the y variable is directly accessible. So you put W2 equal to 1. Oh, sorry. You put W2 equal to 1. But when a variable is only accessible by taking a Lie bracket of order of length 2 here, then you put W3 equal to, and etc., etc. So it means that the definition of the Subramanian weight of some coordinate is a kind of complexity of how you can realize this coordinate. It is the length, the necessary length, the minimal length of Lie brackets that is necessary to reach this coordinate. This is the definition of Subramanian weights. And in terms of Subramanian weights, the homogeneous dimension is also exactly the sum of Subramanian weights. This is why, for instance, in the Riemannian situation, all weights are equal to 1, and in that case, the Hausdorff dimension is the usual topological dimension. But as soon as you are in the Sub-Riemannian situation, the Hausdorff dimension is always strictly greater than the topological dimension, always. For instance, in the 3D contact case, the Hausdorff dimension is equal to 4, which is 1 more than the topological dimension. And in the Martinet case, you have Q equal 5 along the Martinet surface, but 4 outside. Okay, so now we have our operator delta, we have a measure mu, so we can define the associated heat kernel. The heat kernel is as usual, it is the density of the Schwarz kernel of the semi-group generated by delta with respect to the measure mu. What is known? What is already known about that? Many things, of course. Many things are known about the heat kernel. In particular, lower and upper exponential estimates are well known, stating that, so with a double inequality and up to constants, the heat kernel taken at time t and for two points q and q prime is always estimated by some exponential term, exponential minus the distance, Subremanian distance square divided by t, and all of that divided by t to the power q of q divided by 2. Recall that q of q is the Hausdorff dimension, at least whenever q is regular. So such estimates are well known and date back, for instance, to Varopoulos in the 80s. Well, actually, there is. I think there is Adam Sikora in the audience. So I would like to quote an excellent paper by Thierry Coulon and Adam Sikora, who make a very, very good point on exponential estimates for heat kernels, not only in the Riemannian case. Our first objective here will be to establish small time expansions for the heat kernel near the diagonal. I will come to that point in one moment. What is the interest of that? The interest of that is that from this knowledge, we want to be able to derive Weyl laws, local and micro-local Weyl laws. That is, in the self-adjoint case, that is for a true Subremanian Laplacian, such a Laplacian has a discrete spectrum, of course, real and discrete spectrum, with eigenvalues lambda j that are going to the infinity. Associated to it, you can consider an orthonormal eigenbasis phi j. And what you want to compute is an expansion of the trace. You want to consider the trace of f times the semi-group, which is this integral of f against the heat kernel, which is also by the Mercer theorem an infinite sum, like that. And you would like to be able to compute an expansion for small times of that guy. And from that knowledge, and thanks to general theorems like the Karamata-Tauberian theorem, you will be able to infer the asymptotics of the spectral Weyl counting function, which is the number of eigenvalues less than lambda. What is already known about that is the very famous result by Pfefferman and Fong in the 80s, saying that n of lambda is upper estimated and you have estimates, double inequalities for n of lambda, saying, for instance, that in the regular case, in the equiregular case, n of lambda has a double inequality with lambda to the power q, which is the Hausdorff dimension. But actually, this kind of estimate was already known by Métivier, and at the end of the 70s, Métivier proved the equivalence, proved that n of lambda is equivalent to some constant times lambda to some power q. And so more or less we are going to go actually much further than this result by Pfefferman and Fong. And we will also give geometric interpretations of the constants. In turn, we will establish also quantum ergodicity properties, that is, describe the behavior of the probability measures phi j squared in mu for high frequencies, that is when lambda j is going to the infinity. Okay, so an object of interest, and that I must absolutely define before continuing, is the concept of nilpotentization of the Subremanian structure at a given point q. So in one word, so this is this object that we will denote with a hat at q. In one word, this object, the nilpotentization of the Subremanian structure at q, is defined as the Gromov-Hausdorff tangent space. The Gromov-Hausdorff tangent space is exactly the good notion of what is a tangent space in Subremanian geometry. Now, you can define it in a so-called privileged coordinates, which are exponential coordinates associated with the vector fields, in which you can identify the nilpotentization of the manifold with Rn, and it is just Rn endowed with a family of dilations. And the dilations are kind of homotheties, but in which the homothéty is different for each coordinate. You can see that the homothetic factor is nothing else but epsilon to the power, which is the Subremanian weight. These are the dilations. So the nilpotentization is this structure, which is Rn, endowed with the family of dilations. We can also define the nilpotentization of the vector fields xi, which are kinds of first-order approximations, but not first-order approximations in the usual Taylor meaning, but with a non-holonomic meaning, because we need to take into account the fact that there are weights which are not equal to 1 along each coordinate. So it is a kind of non-holonomic first-order approximation. It happens that this is exactly the good notion of the tangent space. And this is the corresponding notion of the usual Riemannian tangent space, but here in Subremanian geometry. Well, so now that we have this nilpotentization, we can also define as well the nilpotentized Laplacian, which is defined as the sum of squares of the nilpotentized vector fields. And so, consequently, we have as well a heat kernel, which we call the nilpotentized heat kernel at the point Q. It depends on Q. All of that depends on Q in a non-trivial way. And by the way, we can notice that the nilpotentization of the heat kernel is homogeneous, but with respect to the dilations. You see here the obvious adaptation to the dilations of the usual homogeneity relation that you know in the Riemannian case. Now, a first result is what we call the fundamental lemma, which gives you exactly a full asymptotic expansion in small time of the heat kernel. So it says that T to the good power, which is Q at Q over 2, of E of the heat kernel near the diagonal. We are near the diagonal, and we have here a full asymptotic expansion, the first term of which is exactly the nilpotentization of the heat kernel. So it says more or less that you have a kind of Taylor expansion, the first term of which is the nilpotentization, which is completely to be expected. This asymptotic expansion in small time is actually in C-infinite topology, meaning that it is valid also for all possible time derivatives of the heat kernel. It is done at any possible Q. I mean, Q need not be a regular point, but actually when Q is regular, then moreover, the above asymptotic expansion is locally uniform. And this generalizes former results by Métivier at the end of the 70s, and a result by Benarous at the end of the 80s, who established a similar expansion, but along the diagonal. So here, the fact that we estimate this expansion near the diagonal is a step forward, is an important actually step forward, because as we will see, it will enable us to derive micro-local Weyl laws and also local Weyl laws for singular structures, which is not possible if you only have at your disposal expansions along the diagonal. As an example anyway, but it was already known since a long time, if you look at the kernel along the diagonal, this expansion tells you in particular that along the diagonal in small time, the heat kernel is equivalent to the nilpotentized heat kernel at time 1 divided by the good power of T to the power Q of Q divided by 2. And this is already sufficient in order to derive the local Weyl law, actually. But let me maybe give one word on how to prove, how to establish such a result. The idea of proof, in order to establish at least the main term, is not very difficult, because you consider renormalization by dilations delta of the Subramanian Laplacians, or of the Hörmander operator delta epsilon. Associated to it, you have a heat kernel depending on epsilon, And just by the Trotter-Kato theorem, you have convergence in a distribution with a distribution meaning of the heat kernel. But of course, what we would like is to have much stronger than that. We would like to have a convergence in C infinite, not in the distributional sense. But in order to pass from convergence in distributions to convergence in C infinite, it suffices to use the property of Montel space of C infinite. I mean, all bounded closed subsets are compact in C infinite. And to get this property that the family of E epsilon is uniformly bounded in C infinite, you just have to use local subelliptic estimates, and that's all. So thanks to local subelliptic estimates, you find that indeed this family is bounded in C infinite, and so you get the convergence. This is almost for free, actually. Also, what we need, and what is maybe less known, is that you also need to develop a hypoelliptic version of the famous CAC principle, saying that actually the asymptotics of heat kernels is purely local. So this quite simple argument gives you almost for free the first term in the asymptotic expansion. Actually, to get the full expansion, unexpectedly, it is much more difficult, very much more difficult. What we do is that we start from the Duhamel formula for the summing groups, okay, and then we expand the integral in the Duhamel formula, obtaining a series of convolutions, right? So all the operators here, Ci, are just defined by successive convolutions involving the semi-group of the nilpotentized Laplacian, with some operators here that come from the development of delta epsilon. And then we want to take Schwarz kernels in this expansion. But here, the very big difficulty is to prove that all operators Ci of t are smoothing. And since they are defined by convolutions with the nilpotentized semi-group, what you require here is actually you need global smoothing properties of the semi-group. And this is what is very difficult. You need global, not only local. Also, you will need global continuous embeddings. And so here is the main difficulty, which is very long and technical to overcome. Actually, we need to work also in Sobolev spaces with polynomial weights, as did Ekman with Martin Eirer some years ago. And we also need to use what we use in particular here is the Kanai transform. I mean, we use the finite propagation speed for wave equations in the Subremanian context. And from that, and thanks to a trick developed years ago by Chigger, Gromov, and Taylor, also much improved by Coulomb and Sikora, thanks to Fragment-Lindelöf arguments, we can indeed derive the desired global smoothing properties. But this is very not easy to do that. Okay, so once we have these asymptotics, well, we can define an interesting object, which is what we call the local Weyl measure. So what is this measure? This measure is just the weak limit as time is going to 0 of the heat kernel that you renormalize, right? So this object, whenever the limit exists, gives you exactly a measure. And this measure, we call it the Weyl measure. So here is the local version of the Weyl measure, but this is the version on the base, I mean on the manifold. Actually, we can also define a probability measure in the cotangent bundle that we call the microlocal Weyl measure, but I will not go into details here. So by the way, this object has very good properties, very good intrinsic properties, and it gives an intrinsic measure in Subremanian geometry, which is also a topic in itself. By usual Tauberian theorem, the local Weyl measure can also be equivalently defined as the weak limit of some Cesaro means. I mean, you take the Cesaro mean associated with the sequence of probability measures phi squared mu, and you take the Cesaro mean of that, you obtain the same object. So this is why you feel that studying this object, the local Weyl measure, will in turn give us some information on the high frequency behavior of the eigenfunctions. This is the interest. So now, what we can say, first, in the regular case, in the equiregular case, I mean, when the SR flag, the Subremanian flag, is everywhere regular, then the local Weyl measure always exists. It is a smooth measure, and this smooth measure is given exactly in terms of the nilpotentization of the heat kernel. Of course, this is not a surprise, and actually it is completely obvious, because from the fundamental lemma just applied along the diagonal, which was already known much before, you have t to the power q divided by 2 of the heat kernel along the diagonal that converges to E hat. So you obtain immediately this result. And in turn, you can obtain the asymptotics of the log of the counting Weyl function n of lambda, which is proportional to lambda to the power q divided by 2. So as I said previously, this result was known long time ago by Métivier at the end of the 70s, but what was not known was the exact expression of the constants here. So here, we improve the result by Métivier by giving the expression for the constant and giving it geometric interpretation, because it is exactly given in terms of the nilpotentization, which is the tangent space in some sense. So for instance, in the 3D contact case, the spectral counting function is in lambda square. This is to be compared to the Riemannian case, where you would have a lambda to the power 3/2. So you see that this is because the Hausdorff dimension in the Subremanian case is always strictly greater than the Riemannian dimension. It means that you have more eigenvalues in some sense in the Subremanian case. Okay, so this is the equiregular situation, which is a quite simple situation. By the way, we can also compute the microlocal Weyl law, but I do not give detail here. Let me jump directly to the most exciting singular Subremanian case, in which there are much more surprising issues. So I already defined for the Martinet case and for the Grushin case what is the singular set. The singular set is the set where the Subremanian flag is not regular. I mean, there are some possible jumps in the dimension of the successive elements of the filtration. Or, in other words, the singular set is also the closed set where the homogeneous dimension is strictly greater than the Hausdorff dimension of the regular part. So we immediately feel that we have to introduce a new filtration, which is the filtration before, but that you have to restrict to the singular set. So this is exactly the meaning of this filtration here, because we have to take into account how the successive Lie brackets behave with respect to the tangent space at the singular set S. And following Gromov, who introduced this definition at the end of the 90s, we say that S is an equisingular submanifold of M if all dimensions, so the dimension of the usual filtration, and also the dimensions of the filtration restricted to S are constant. In that case, we say that S is equisingular. And in particular, we can introduce, as we did before, this sum. And this sum can be proved. It is a quite recent result by Ghezzi and Jean 5 years ago. This guy that we denote by Q to some power S is exactly the Hausdorff dimension of S. So QS is the Hausdorff dimension of S. For instance, if we consider the Grushin case, of which the local model is written here, so the singular set is exactly the set x equals 0, I mean the set at which you have a degeneracy. In that case, the Hausdorff dimension of S is equal to 2. It coincides with the Hausdorff dimension of the regular region, which is outside of S. And for the Martinet case, we have exactly the same Hausdorff dimensions and the same singular set. Well, so here is a first result giving you the trace, the expansion of the trace for the Grushin and Martinet case. Let us look at, for instance, the Grushin case. For the Grushin case, we claim that the trace can always be written as an infinite formal series. F1 and F0 are C-infinite function. But you see that the novelty there is that we can see appear a logarithm. There is a logarithm in the trace. And actually, in this expansion, we are even able to compute the two first terms of this expansion. I mean, the terms against logarithm divided by t and the term against 1 over t, which are completely intrinsic objects. So in that case, and it is remarkable, we have an intrinsic two terms expansion. In the Martinet case, the difference is that instead of dividing by t, you divide by t squared. So what is interesting here, for instance, is to see the consequence in terms of local counting of functions. In the Grushin case, the counting functions is in lambda log lambda, and in the Martinet case, the counting Weyl function is in lambda square log lambda. So you see the novelty there is the appearance of this logarithm in the counting Weyl function. Well, actually, by completely other tools, the local Weyl law in the Grushin case is a consequence of results by Mennikov and Chaustrin at the end of the 70s, but only in the Grushin case, because it is completely other methods. But our method used here is actually much more general. And for instance, here we get the Martinet counting Weyl law, which is completely new. And actually, more generally, when S is an equisingular submanifold, we can always compute this trace, and this trace is exactly the generalization of what you saw on the Grushin and Martinet case. So there is, in some sense, there is a part which is coming from the equiregular part, plus a new part which take into account the Hausdorff dimension of the singular set, and with the appearance of a logarithm. You have cases depending on whether the Hausdorff dimension of S is greater or maybe lower than the Hausdorff dimension of the regular part. And for each case, of course, as a consequence of the local Weyl law, we can derive the counting Weyl functions. Actually, this theorem let me maybe pass on that. This theorem can be generalized to much more general situation where you assume that the singular set is witness stratifiable. I mean, there are several possible strata. Witness stratifiable means, in 2 words, that you have a manifold which is, sorry, you have a set which is the union of several manifolds. It is a piecewise manifold in some sense, and it is the meaning of stratifiable. And you assume that all strata are equisingular. Then in that case, you can always compute the local Weyl law, in which, so you see the exact generalization of the theorem before, in which you can see appear the Hausdorff dimensions, all possible Hausdorff dimensions of the strata, with iterated logarithms this time. I mean, this time we can have power of logarithm in the Weyl counting function. Also, I forgot to say that we add here an assumption which says that the horizontal distribution is nilpotentizable. And nilpotentizable means, I wrote it here, nilpotentizable means that locally at every point Q, the horizontal distribution D is diffeomorphic to its nilpotentization. So it means that from the point of view of normal forms, it means that there is only one normal form at the point Q in some sense. Okay. By the way, as a consequence of that result, we obtain quantum ergodicity properties, because when the Hausdorff dimension of the highest strata is greater than or equal to the Hausdorff dimension of the regular region, then as a consequence of that result, it means that the high frequency eigenfunctions do concentrate on the singular set. It means that they may converge to kind of Dirac measures along the singular set S. And for instance, in the Grushin case, we're even able to prove that, at least whenever the singular set is connected with at most one so-called tangency point, then there is only one possible weak limit, which is the Weyl measure. And this property is exactly what is called in the literature quantum ergodicity property. Actually, it is this gives you the first example in Subremanian geometry of a quantum ergodicity result with a limit measure that is a singular measure. So it is a new phenomenon. But actually, even more exciting, and this is an ongoing work, we are able to compute even more exotic Weyl laws in cases where we lose the nilpotentizability assumption. Let me give you some examples. Let us consider this case, which is you recognize a perturbation of the 2 Grushin case. You see, this is a perturbation with some function g of y that we will take flat at 0 in order to generate interesting examples. And so you consider this Subremanian structure with 2 vector fields in R2. And then here you have examples of function g, which are all flat at 0, okay? No, sorry, this one is not flat, but these ones are flat. And in that case, you can see at the right what you obtain as a possible local, as a possible counting Weyl law. So you see that we start to obtain quite exotic Weyl laws. For instance, we can have iterated composition of logarithm, which was a question, because in the previous examples I showed you, there was only one single logarithm. So our question here was, is it possible to obtain some kind of log-log in the counting Weyl law? So the answer is positive. We are able to generate some log-log. And even on the last example I will show you, we can even generate a trace, you see, that which is strongly blowing up when t is equal to 0, like that. And then you obtain, and it is completely non-standard, you obtain a counting Weyl function, which is like the exponential of lambda, which is very not usual. Okay, so I think my time is up. So let me go to my conclusion. The examples I showed you at the end of my talk make one think that maybe we could be able to, if you give me a kind of arbitrary asymptotics, of course, certainly assume making some basic assumptions on it, we think that it is always possible to find, to design a Subramanian case for which the Weyl law has exactly this asymptotics. It is an interesting kind of inverse problem. Another problem is the general problem of finding spectral invariance in Subremanian geometry, and it is of interest from the geometric point of view. For instance, in the Riemannian case, it is known that the successive coefficients of the local Weyl law, I mean the small time asymptotics of the heat kernel, have a nice interpretation in terms of curvature. It is a completely open question to investigate whether the coefficients of the local Weyl law in the Subremanian setting have also an intrinsic interpretation in terms of curvature. It is completely open. Another application that is also quite exciting is to apply knowledge coming from sub-elliptic Laplacians to the study of controllability or observability of that kind of equation. I mean, heat, wave, or Schrödinger equations in which you replace the usual Laplacian with a sub-elliptic Laplacian. For instance, it has been proved very recently by my PhD student Cyril Le Truit that sub-elliptic wave equations are never observable. While if you look at heat and Schrödinger equations, there are also new phenomena with respect to the usual Riemannian setting. For instance, in some situations, sub-elliptic heat and Schrödinger equations can be observable, but contrarily to the Riemannian case, there is a minimal time for controllability or observability. And this kind of completely new phenomenon was shown quite recently by Karine Bochard, Pierre-Marco Canarsa, Michel Dupré, Armand Koenig, and also by Nicolas Burke and Chen-Min Sun in a very recent paper in the Schrödinger case. I mean, it is surprising that for the Schrödinger equation in the sub-elliptic case, there may be a finite propagation of speed, and this is there in their paper. But so these works are very interesting, but at that point, so this is completely ongoing works, we still miss a geometric picture in order to give a geometric interpretation of why there is a minimal time. Such geometric pictures do exist in the Riemannian case. I'm thinking about the famous geometric control condition by Bardos, Lebeau, and Rausch, which is very well known. But this kind of consideration still does not exist in the sub-elliptic setting, and this is probably also one of the most exciting issues that we would like to investigate in the future. Okay, I will stop here, and I thank you very much for your attention.
Enrico?
Thanks a lot for your talk. So, there is any question or comment?
You can raise the hand, guys, the attendees, and then we can give you, I can give you permission to speak.
Yes.
Yeah. Adam, you have permission to speak.
Good. Okay. I'm not sure if my question is actually meaningful, but can you apply these techniques to obtain some results about compact Lie groups?
Yes, absolutely. Compact Lie groups, you mean with a Subremanian structure in it, right?
Yeah, yes. We choose a number of vectors which generates a whole algebra, but which are not gives you full Laplacian.
Yes, it perfectly makes sense, and actually it is a particular case of our study in which, thanks to the Lie group feature that you can have on it, we can even be more specific about the local Weyl law. For instance, in this kind of expansion, which we can be much more specific about the form of the smooth functions f0, f1, and f2. Actually, there are, in the Lie group settings, or in the nilpotent case also, you can find many, how to say, you can have some gaps in these expansions. You have many gaps that you can measure. And by the way, these gaps are interesting because in turn, they permit to define new invariants that have not been investigated until now. So it opens certainly new issues, also to give what we hope to be new spectral invariants on such Lie groups. Yeah.
Okay, thank you.
Other questions or comments?
Hi, I have a question about the last part of your talk where you give information about observability, so also controllability of the control system, yes? Are there any informations in this framework about the minimal energy of the control, which takes you to a given point?
Well, these studies are in some sense to some preliminary studies. So until now, I'm not aware of any study about, for instance, what would be the cost of controllability for realizing the controllability, for instance, in the subelliptic heat equations. No, it does not exist. As far as I know, I mean, and it is true that it is certainly a very, very exciting issue too, because in the Riemannian setting, I mean, when you control a usual heat equation, a Riemannian heat equation, then inside the cost of controllability, you can see emerge some geometric, some constants that have a geometric meaning. And so you are fully right. I did not think about this issue, but for the subelliptic heat equation that was studied, for instance, by Bochard and Canarsa, it could be very great to study if there is a similar observability inequality with a constant inside of which we can get some new geometric information. But I'm not aware of any work in this direction until now.
So nothing is known about the behavior of the energy of the control when time goes to zero, yes, or to the minimal time in your
exactly, yes. Only there is only few knowledge until now. And even for the minimal time, it is even not know what is the sharp minimal time. I mean, let me maybe explain what is the sharp or the optimal minimal time. In the Riemannian case, we know that the minimal time for controlling a wave equation is the so-called GCC time, geometric control condition time. That is, you are given a domain, capital omega, inside of which you put a smaller subdomain, small omega, on which you put the observability or the control. Then the GCC, let me recall it quickly, the GCC stipulates that every geodesic ray propagating in the billiard, that is capital omega, and reflecting at the boundary of capital omega according to the laws of classical optics, all such rays should meet the control subset small omega within a time capital T, say. Well, so now we define the minimal time capital T so that every ray has met small omega. And this minimal time T is exactly the minimal time for controlling the wave equations. This very, very striking result was proved by Bardos, Lebeau, and Rauch at the beginning of the 90s, and it is very well known. But until now, we do not have available such a beautiful result in the Subremanian context. Well, this is there that we miss a geometric picture, because in the Subremanian context, in some sense, the geodesic flow, which becomes here the Subremanian geodesic flow, is not sufficient in order to characterize observability, because also the, how to say that, also the flows generated by Lie brackets comes into the picture. For instance, in the contact case, you have this first Lie bracket, which was dz, which generates the missing direction, right? Well, actually, and roughly speaking, the flow of this first Lie bracket has a name in geometry. It is called the Reb flow. Reb is written here. It is called the Reb flow. And actually, even though nothing is proved until now, almost nothing is proven until now, we feel that also the Reb geodesic flow comes into the picture, and we should also consider a kind of GCC also associated to this Reb flow. But this is only a guess. Nothing is proved there until now.
Thank you.
You're welcome.
Other questions or comments? Well, if not, I leave the ball to Daniel for closing the meeting and possibly inviting people to the coffee break.
Yeah, thanks, Enrico. Yeah, thank you, Emmanuel, for this nice talk. And you should all have received an invitation to the coffee break. It's another Zoom seminar. Please join. Yeah, I hope to see you there. I will close now the session.
See you soon.
Yeah, see you. Thank you. Bye.